Hello everyone, welcome back to our channel. Let's discuss the next topic, that is spin-spin coupling. In the last video, we had a clear discussion on what are the factors which can influences the chemical shift values, and also we have seen some of the chemical shift values of different kinds of the protons as per the functional group. Okay. Now the next topic is what? Spin-spin coupling or spin-spin splitting. Why we are saying it is splitting? For your easy understanding, again I am going to take the same hypothetical molecule. In the hypothetical molecule, we are having two non-equivalent sets of protons. One Fresnel frequency is 60,000,080 Hz. The second one Fresnel frequency is 100 Hz. In order to simplify the spectrum length, what we are doing, we are adding the tetramethylsilane as a standard. So the peak is going to be considered as the 0. So with reference to this one, we are going to get two signals. One is for the H1 and one is for the H2. So this is the concept according to the quantum or classical approach of NMR spectroscopy. Right, till now we have studied this one only. Now what the people are saying, if you see the real spectra of this molecule, what we are observing, the H1 is appeared in the form of two lines, then H2 is also appeared in the form of two lines. We are expecting what? One line for H1 and one line for H2. But what is the reality? It is becoming 2 for H1 and 2 for H2. That's why what we are observing, one signal is converted into two or not. So this is commonly called as what? Splitting. So what is the definition? Cleavage of proton NMR signal or appearance of proton NMR signal with more than one line is commonly called as a splitting of signal. So what is the conclusion? The reality is something else. For every signal is going to be splitted. The splitting phenomena takes place. Splitting means cleavage of proton NMR signal with more than one line. So in this case we are identifying two lines, but some cases more than two lines are also possible. Okay. So why the splitting is possible? What is the reason for the splitting? So now the people are saying the splitting is due to the mutual influence of the spins of the neighboring nuclei, is commonly called as spin-spin splitting or spin-spin coupling. What is the main reason? The influence of the neighboring proton spin. It means H1 and H2 are not independent. H1 and H2 are dependent. H1 spin influences the H2 proton. H2 spin influences the H1 proton. Because of that reason, coupling between H1 and H2 spins takes place. That coupling is commonly called as spin-spin coupling or spin-spin splitting. Why we are saying it is a splitting? Because of the coupling phenomena, the NMR signal is going to be splitted. Appearance of the NMR signal with more than one line is possible because of the coupling. Which coupling? Spin-spin coupling. Neighboring hid protons spins influence is commonly called as spin-spin coupling or spin-spin splitting. The concept is very simple. Try to understand in a simple manner. Okay? Assume that the H1 proton precisional frequency is 60,000,000 H. See this one. Here we have assumed what? H1 precisional frequency is 60,000,000 Hz. We are expecting, right? Then see the reality. What the reality is. the H1 proton is going to influenced by the spin of the H2. Okay, already we know that the proton have two spins, upward spin and downward spin. So at one time the H1 nucleus takes the upward spin of the H2. At another time the H1 nucleus takes the downward spin of the H2 nucleus. See this one, upward spin means what? It is parallel to the direction of the external magnetic field or not. So total field is going to be what? Addition or not? So addition means precessional frequency increases. Thereby chemical shift values increases. Here this is downward spin means what? It is opposing the strength of the external magnetic field or not. So it is cancelling the strength of the external magnetic field. That's why the net field at H1 will be less or not. Net field less means precessional frequency will be decreases. The simple concept is, if H1 proton is influenced by the upward spin of the H2 proton, the precessional frequency of the H1 will be increases. That's why this one can give one signal. Similarly, if the H1 proton is influenced by the downward spin of the H2 proton, because of the cancellation of the fields, what happens? The precessional frequency of H1 will be decreases. That's why at 80 we will get one signal, at 120 we will get another signal. So previously we have assumed what? At 100 we will get the signal. So we are not going to get the signal at 100. We are going to get the signal more than 100 and going to get the signal less than 100. That's why the H1 proton real lines are going to be 2. Similarly, if the H2 proton is going to identify the upward spin of the H1, the precessional frequency increases. If the H2 proton identify the downward fin of the H1, thereby precessional frequency decreases. So we are going to get what? Two different signals. So this is the concept of what we call it as spin-spin coupling or spin-spin splitting. The people introduced spin-spin. The spin of the hydrogen is going to influenced by the neighboring proton spin. Okay, one time upward, one time downward. Upward means overall net field is going to be higher. That's why precessional frequency is higher. So chemical shift values are going to become higher. Okay. So according to the concept of spin-spin coupling, we are going to get the splitting phenomena. Okay. So whatever the thing which we have discussed right now, that one has given in the form of a paragraph for your understanding. Okay. The same thing. Okay. This point is very, very important. Coupling between all types of neighboring nuclei takes place, but coupling between only chemically non-equivalent sets of protons splits NMR signal in the spectrum. Spin-spin couplings are takes place through the intervening covalent bonds. That is, spin interaction information transmitted by the intervening covalent bond electrons only. With increasing the bonding between the neighboring protons, the strength of the coupling is going to be decreases. Up to the third connection, usually couplings are stronger. If we have more than 3 bonds, the couplings are going to become lesser. In solid state NMR, coupling interactions of neighboring protons are through the space, not through the bonds. So, how can we see this paragraph? Already we know that all kinds of the neighboring nuclei can be influenced by each other. That is commonly called as coupling. Okay, so every proton or every spin active nucleus is going to coupled with the adjacent spin active nucleus. Now the question is, each and every kind of coupling can split the signal? No. What the people are saying, whenever the coupling is takes place between two non-equivalent sets of protons, then only splitting of NMR signal takes place. See in the example clearly. In this particular example, we are seeing H1 is converted into two signals, H2 is converted into two signals. Why these are splitting? Because the H1 and H2 are non-equivalent sets of protons. Okay. So whenever the coupling is possible between two different non-equivalent sets of protons, then only the spin-spin coupling is going to lead to the splitting pattern. Okay. So remember this line. The splitting is only possible because of the interactions or couplings between the non-equivalent sets of protons. Okay. That is. So let's see. In the example, we are having only two protons. If we have more than two protons, how can we get the signal? If we are having only two protons means the intensity of both the signals will be same. If you have more than one proton, see this one. In this molecule, we are having H1 only one proton, but adjacent we are having two protons. So if the number of protons increases, then what happens? The intensity of the signals will be increases. What the people are saying? 1 is to 2 is to 1 ratio. So in this way, we are going to get the signal. The percentage of spin orientation. Say this one. Two times we are getting the spin orientation or not. Why? Because for H2 we are having upward and downward this H2, and again this H2 also we have two spins. The probability if we see, we are going to get what? Four probabilities, but second and third are becoming equal or not. That's why it is taking 50%. So the center one is going to be the double of the corner ones. Okay, then how can we easily identify the number of signals in a particular non-equivalent sets of protons? For that purpose, we are having one concept commonly called as multiplicity. Multiplicity means what? Number of lines in NMR signal is commonly called as multiplicity. The same hypothetical molecule, here we are getting two signals or not. So the number of lines in a NMR signal is commonly called as multiplicity. If you take H1 proton, we are getting how many lines? Two lines. So the multiplicity of H1 will become 2. The H2 is splitting into two signals. That's why the multiplicity of H2 will be 2. So how can we predict the multiplicity? Multiplicity means what? The number of lines in the spectrum, right? So for that purpose, we are using a rule commonly called as n plus 1 rule. The n indicates what? Number of chemically non-equivalent neighboringhood protons for the reference protons. N is simply non-equivalent sets of protons. See this one. This is the molecule which we are having. In this molecule, we have two different sets of protons or not. This is H1 and H2. Both are chemically non-equivalent. That's why splitting phenomena takes place. So we will observe the multiplicity. Multiplicity means number of signal. So if you take H1, if you want to identify the multiplicity of H1, we need to dependent on what? H2. How many H2 are there? Only one H2 or not? That's why n is going to becoming 1. Okay, 1 plus 1 is 2 lines. So if you want to take the multiplicity of H2, you need to dependent on what? You need to dependent on H1. H1 are how many? Only 1. So 1 plus 1 is going to 2. So here you can clearly observe. See this one. If you want to see the multiplicity of H1, how many number of protons are there on the adjacent carbon. 2 protons are not. So N is going to be 2. So 2 plus 1 is giving 3. The multiplicity of H1 will becoming 3. So for this one, how many H1 are there? Only one H1. So N will become 1. 1 plus 1 becoming 2 lines. So in this way we can calculate the multiplicity. See, in this case, if you want to see the multiplicity of H1, how many protons, adjacent protons are there? 3 protons are not. So N will become 3. 3 plus 1 will give 4. Okay. So in this way we can identify the number of lines in a NMR spectra. Okay. By using N plus 1 rule. See this. Here is a molecule. CH3, it is not connected to any adjacent carbon containing the protons. That way always we will get the single signal. But if you take these two are chemically non-equivalent or not. So how can we identify the signal? So at the B set, we have two protons. What are the number of signals for that CH2? The splitting pattern of the two protons dependent on what? Adjacent CH3. So adjacent we are having 3. So 3 plus 1 will become what? 4. That's why 4 lines for these two protons. So if we consider the CH3, we need to dependent on what? These two, adjacent 2. So 2 plus 1 become 3. So 3 lines we will get for the compound. So in this way we can identify the number of lines for each and every set of protons. Okay. Now come to the intensity ratio of the signals. We are saying that more than one signal, it may be 2, 3, 4, 5, 6, like that, no? So what will be the intensity? For that purpose, we are using a triangle commonly called as Pascal triangle. According to the Pascal triangle, see this one. If you see these values, we will come up with one triangle or not. This is commonly called as Pascal triangle. So if you have only one signal, this will become like this one. If we have two lines, 1 is to 1 ratio. If we have 3 lines, 1 is to 2 is to 1 ratio. If we have 4 lines, 1, 3, 3, 1. If we have 5 lines, 6 lines. So how we are getting this one? See this. If we have 2 lines, 1 is to 1 ratio. If we have 3 line, terminal 1, 1, how you can get the 2? Simply 1 plus 1 becoming 2. So if you want to go for 4, terminal 1, 1. So 2 plus 1, 3. 2 plus 1, 3. 3 plus 1, 4. 3 plus 1, 4. 3 plus 3, 6. So 1 line means singlet. 2 line means doublet. 3 lines means triplet. 4 lines means quartet. 5 lines means pentet. 6 lines means sextet. 7 lines means septet. Like that we can give the nomenclature in NMR spectrum. Okay, according to the Pascal triangle. We have second criteria that is also commonly called as binomial expansion. A plus B whole power n. N is number of neighboring hood protons. If there is no neighboring hood protons, only one signal, that is the single. If you have only one neighboring hood proton like this, you will get doublet, 1 is to 1 ratio, n equal to 1. If you have two neighboring protons like this, we will get a plus b whole square formula. A square plus 2ab plus b square. So what will be the ratio? 1 is to 2 is to 1. If we have three neighboring protons, a plus b whole cube, a cube plus 3a square b plus 3ab square plus b cube. So a equal to 1, b equal to 1. So 1 is to 3 is to 3 is to 1. So in this way we are going to get the intensity ratio. You need not to remember both the expressions, just follow the Pascal triangle. Based on that you can easily identify the intensity ratio of the signal. Okay, so this is all about the spin coupling multiplicity of NMR signal. So in the next class we will have a discussion on coupling constant and what are the types of coupling we will observe in NMR spectroscopy. Okay, thank you.